A good day to anyone who is watching. We are Group 15 from Section 32, and today our topic is solving systems of linear equation, more specifically, unique solutions. Our group members consist of Kong Zhenting, Jia Liang, Pang Kai Jie, and myself, Yojun Axel. Now I will be explaining what is solving systems of linear equations. Moving on to the topic that we're going to be discussing today, which is solving systems of linear equation. There are two types of ways to solve this, which is using the elementary row operations or the matrix method. To be more precise, elementary row operations consists of cos, elimination method. As for the matrix method, there are two, which is Cramer rule and the inverse matrix method. All these will be explained by my key members later. The linear equations can be written as the one down below, with m as the linear equation and n as the number of variables. There are actually two types of systems which I will be talking about, which are the non-homogeneous and the homogeneous. Now, we'll be moving on to that. These are the two types of systems I will be talking about today, which is the homogeneous and the non-homogeneous. The homogeneous system is the system of linear equation where all the constant terms are equal to 0, which is x equals to 0. A trait of the homogeneous system. For example, like all these equations right here, we have b, which is right here, has to be 0. That's one of the traits of the homogeneous system. Now, moving on to the non-homogeneous system, which is actually just the opposite, which is a system of linear equation where all the constant terms are not equal to 0, meaning that our b here can be any type of number. Like, for instance, 1, 2, 3. It will also be counted as the non-homogeneous system. The non-homogeneous system consists of many types of solutions, which is the unique solution, which I will be talking about right now, and many types of solutions, and the no solution. For the unique solution, there will be only one solution, unlike the many solutions where they are infinite. And for a unique solution to happen, it has to meet the terms right here, which is the PA, which is the rank of matrix of A, has to be the same as the rank of matrix of A and B, and it also has to be the same as the number of variables. Now I'll pass it on to my group mates to explain more about the unique solution and how to do it.
Good evening everyone, my name is Kong Zhenting. This is example 2 which talk about solving system of linear equation. The question is given like this: find the value of k so that the system has a unique solution. The question already provided the linear system, which is 3. So, to solve this kind of question, we need to convert all of the linear equation into augmented matrix form. So we can see that 1s1 plus 1s2 plus 1s3 equal to 2 will become 1, 1, 1, 2 at here. For another row, it's same operation. The 2s1 plus 3s2 plus 2s3 will equal to 5, which is same to 2, 3, 2, 5. So after we convert all of the linear equation into augmented matrix form, we need to using the elementary row operation to get the echelon form. So here loop become 0. So the first operation is row 2 minus 2 times row 1 will become row 2. So we can see this 2 minus 2 times 1 will become 0. For another element inside this row, they are going to same operation. So another operation is row 3 minus row 2. So 2 minus 2 will become 0, 3 minus 3 becomes 0, k squared minus 1 minus 2 will become k squared minus 3. And the last, k plus 1 minus 5 will become k minus 4. So after we get our echelon form, we need to know that if the system has a unit solution, the rank of matrix A will be equal to the rank of matrix A vertical bar B, and the number of variables in this question that all over will be 3. So to make sure its unit solution, we know that this part cannot be 0. To make sure we has a non-zero row inside our matrix. So k squared minus 3 will not become 0. So k squared won't become 3. So the final answer is k not equal to plus minus 3.
Good evening, my name is Jia Liang. So today, basically, I will talk about the type of solutions for system of linear equations. I will talk about only one type of the solution, which is unit solution. So without further ado, let us start. Solve the following system of equation by using Gauss elimination method. And the question has provided us the linear system. So in order to see whether the linear equation have a unit solution or not, we need to find out the epsilon matrix first, and see whether have it fits the rule for unit solution or not. Okay, let us start doing the Gauss elimination method first. This method I have already standby for doing for the solution. Now we will go through for the solution. So we try out for the augmented matrix form first. The augmented matrix form try out from this equation. So what we need to do is to get the row here become 0 and get here this 3 value, get a 1 value like the final answer here. So how we do it? First, in order to get this 3 to become 0, row 2 minus 3 row 1. So 3 minus 3 times 1 will get 0. And set the same thing here. Like 8 minus 3 times 2 will get 2. 9 minus 3 times negative 1 will get 12, and the same. And also for here, we need to change to 0, right? So in order to get 0, row 3 minus 2 row 1. So 2 minus 2 times 1 will get 0. And negative 1 minus 2 times 2, negative 1 minus 4 will get negative 5. And the same thing here. After that, we already have this. And now we need to get these 2 value become 1. So we just half the row 2 and we get it. And the same thing here. After that, now we have this one. We need to get the 0 value here. Because in order to have the 1 value from here, we need to finish first for the previous value here. We need to get the 0 first. So to get the 0, negative y, obviously we see here got 1, right? So easy to get the 0. Row 3 plus 5 times row 2. So negative 5 plus 5 times 1 will get 0. And also remember for the behind here. After that, finally, we just remain this term 34. In order to get 1, we just divide by 34. So 1 over 34 times R3 will get 1. So now we already have the epsilon metric form, the epsilon form. As you see here, 0 this. So from this epsilon form here, we can see that the number of non-zero row in epsilon matrix A in excellent matrix A is equal to how much? 1, 2, 3, right? Non-zero equal to 3. And also for number of non-zero in excellent matrix of A is B, with this full term, it's also the same thing. It doesn't affect anything. It's also 3. And the number of variables for this linear system is also 3. X, Y, and Z, right? So, since we fulfill this rule, we can conclude that the system have a unique solution. Yeah. So we have a unique solution because we will get this equation from here. X plus 2y minus z equal to 6, and y plus 6 times z equal to -4, and z equal to -1. So when z equal to -1, y plus, we just substitute back the value here. And after we get the value of y and z, substitute back at the value inside this equation, we will get the x. So the solution we get are x equal to 1, and y equal to 2, and z equal to -1. This is the unique solution for this linear system.
Hi, I'm Pangajet. Now I would like to present the example 3 for unique solution. First, the question asks to find the value of A such that the system has a unique solution. So first, we need to transfer these 3 equations into argumental matrix form like this. Then we reduce this to row echelon form by using the Gaussian elimination. Row echelon form is these 3 numbers become 0. So first we see the row 2. Row 2 become R2 minus 2 R1, then we get 2 minus 2 times 1 become 0, and 3 minus 2 times 2 become -1, then 3 and -1. Then we see the row 3. Row 3 become R3 plus 4 R1, then become 0, 3, k squared minus 13, k plus 5, and then see the row 2. Row 2 become negative R2, then we get 0, 1, -3, and 1. Then last we see the row 3. Row 3 become R3 minus 3 R2. Then we get 0, 0, k squared minus 4, and k plus 2. So now we get the row echelon form. The question asks to find the value for k when the system has a unique solution. So we need to check the value of PA, PAB, and number of variables. System has a unique solution when PA equal to PAB and equal to number of variables. Since this equation has 3 number of variables, which is x, y, and z, so PF and PAB must equal to 3. So this number will not equal to 0. So k squared minus 4 not equal to 0, and solve this, then we get k not equal to -2 and k not equal to 2. Then the question B asks to solve the system of equation if k equal to 3. Then we write the 3 equations first, which is x plus 2y minus z equal to 1, and y minus 3z equal to 1, and then k squared minus 4 z equal to k plus 2. Then the substitute k value of 3 into this, and we get z equal to 1, and solve this. Then finally we get the solution is x equal to -6, y equal to 4, and z equal to 1. So that's all for our presentation. This vision is come from book 15, and thank you for watching.